Hi everyone, I'm Mike Ruberry, an engineer at Facebook working on PyTorch, and I'm going to be talking to you about how we're making PyTorch more NumPy compatible. In this short talk, there'll be 3 parts. First, I'll describe what it means for PyTorch to be NumPy compatible and what our goals are. In the second part, I'll talk about the many new and updated operators we have in PyTorch 1.7 that make it the most NumPy compatible release of PyTorch yet. And in the third part, I'll talk briefly about where we're going in PyTorch 1.8 and beyond. So let's get started by talking about what it means for PyTorch to be NumPy compatible. For those of you who don't know, NumPy is a popular Python package for working on arrays, or what PyTorch would call tensors. Its API is well known, and that makes it familiar to many users coming to PyTorch for the first time. By making PyTorch compatible with NumPy, we means it implements the same functions that NumPy does, and that the behavior of those functions is pretty much the same in PyTorch and in NumPy. This means that people familiar with NumPy will already be familiar with PyTorch, making it intuitive and easy to use. This should let people spend less time looking at documentation and more time developing their programs. The idea of NumPy-compatible PyTorch is not new. From the beginning, PyTorch was designed to be like NumPy, and as these code snippets show, both packages are extremely similar today. There are small differences between PyTorch and NumPy, however. For example, as previously mentioned, what NumPy calls arrays, PyTorch calls tensors. In this snippet, we also see that PyTorch is a little more explicit about data types, requiring that the tensor B be specified as containing floating point values before the exponential function can be called on it. Now, we might think that the goal of NumPy compatibility is to eliminate all differences between PyTorch and NumPy, but that's actually not the case. There will always be differences between PyTorch and NumPy because they focus on different scenarios. PyTorch, for example, is designed to run on multiple devices, not just on the CPU. It also runs, for example, on GPUs, TPUs, mobile devices, and custom ASICs. PyTorch is also designed to run neural networks. And neural networks typically run in a lower floating point precision than scientific programs do. Finally, PyTorch is designed to support AutoGrad, which has its own specific set of requirements. For example, to compute a backwards pass properly, PyTorch has to save intermediate computations. Focusing on scenarios like this means that PyTorch and NumPy will never be exactly the same, but we can still strive to make PyTorch as similar to NumPy as possible. Now let's talk about how we've done that in PyTorch 1.7 and why it's the most NumPy-compatible version of PyTorch we've ever released. It's because we've added a ton of new operators that NumPy had, but PyTorch was missing, and even updated some older PyTorch operators whose behavior was different than their corresponding counterparts in NumPy. For example, we've added a slew of functionality related to fast Fourier transforms. We have new functions for computing statistics, like torch.quantile. We have helper functions for manipulating tensors, like hstack, vstack, and dstack. We even have the 0th order modified Bessel function of the first kind. We also updated some operators, like division, for example, in PyTorch is now compatible with division in NumPy and Python 3, always performing a true division instead of sometimes performing an integer division. In total, we modified over 65 operators in PyTorch 1.7. Now, where are we going? Well, in PyTorch 1.8, we expect to add or modify another 38 operators. We expect to expand on 2 new modules too. The torch.ft module, which contains the fast Fourier functionality that I already mentioned, and the torch.linalg module, which will contain linear algebra functionality. And we also plan to keep our community engaged. At the time of writing, we had 14 active community contributors, and since then we've already added several more. This is a great opportunity for you to get involved too. If there's a function in NumPy or SciPy that you'd like to see in PyTorch, let us know by filing an issue on our GitHub. And if you'd like to get involved by contributing an operator to PyTorch, see the linked issue to get started. A huge thank you again to our community contributors. This slide is already out of date, which is unfortunate, but it's been a great experience working with our fantastic PyTorch community to make PyTorch more NumPy compatible and ultimately to make it easier to use. So thank you again for all our active contributors as of October of this year for their help and support. And thank you for listening to this talk about how we're making PyTorch more NumPy compatible.